Hello and welcome back to part 3 of my Godot tiles tutorial. In this video I will create a grid for the tiles with configurable tile subdivisions. First I need a variable for the grid subdivisions. I export it so that I can edit it in the inspector. Next I update the calculation for the tile size to take the grid subdivisions into account. For that, I divide the total image size by the grid size. So for example, if we have a grid size of 3, then each tile will be 1/3 of the total image size. To prevent each tile to display the whole image, I use sprite regions. With that, I'm able to only display a portion of the image by using an XY coordinate and a width and a height. To be able to iterate over the grid, I update the calculation by multiplying the region result by an arbitrary number. Later I can use these numbers in a loop to determine the X and Y position for the region and therefore the column and the row of the tile. If I set this value to 1, we get the top middle part of the image. And if I set it to 2, we get the top right corner. The Y position works the same way. To be able to comfortably edit these values, I create a new vector to cell. Then I iterate over all grid subdivisions, in my case 3 to the power of 2 equals 9. I create the instance and assign the cell. For that, I create a new method getCell, pass it the current value of I in the loop, and convert the one-dimensional index of my array into a two-dimensional position. For this, I use the modulo operator to get the remainder of I divided by grid subdivisions and round it down, which in my case is either 0, 1 or 2 for the column, and for the row I simply divide I by the grid subdivisions, which also results in 0, 1 or 2 for the row index. That means if I is 0, we get a position of 0, 0. If I is equal to 2, we get a vector of 2 and 0, because 2 divided by 3 is 0 point something and rounded down is 0. If I is 3, that means the fourth position in the array, then I modulo grid subdivisions is equal to 0 again, and 3 divided by 3 equals 1, so we are in the second row. This concept is useful if you need to convert a two-dimensional array into a one-dimensional list. Next, I create a separate variable for the region and use the static calculation from below. Next, I need the position for the instance. For this, I create another new method, getPosition, which works with the current loop index like getCell and returns a position in world space. For this, I get the cell position in our virtual grid and multiply these values with the tile sizes to get the tile position in world space. Now I can replace my static x and y values with the calculated ones. And with that we can see the complete image again, but this time composed out of 9 tiles. The gaps between the tiles are the result of the low resolution of the source image. If you use a higher resolution image, those gaps won't be visible. These are rounding errors, but this is good for now, because with that you can see each tile individually. To test the system, I set the grid subdivisions to 4 inside the inspector, and now you can see that the gaps are gone, because now we have an even tiling across all the pixels. And on odd subdivision values, you get rounding errors on small images, like I said. Finally, I create a new variable, scaled tile size, so that I don't have to divide the tile size by the image scale all the time. In the next video, I will take care that the tile positions getting randomized. Thanks for watching, until then, bye.